Welcome to another session of Everyday Mathematics. Here at Everyday Mathematics, we do enjoy solving the harder problems, but also we do appreciate and see the beauty in the simpler problems. So today's problem comes from the MIT 2022 Integration B Quarterfinal number 1, problem number 2. And the problem is limit as n tends to infinity of the product of n and the integral of tan to the power n x from 0 to pi over 4. This is a very interesting problem, and it's my hope and desire that you'd also enjoy the solution that we propose here today. So before I start on the solution, I'd like to shout out to our subscribers. We are really growing, we're excited. And thank you so much to all our subscribers for all the support that you continue to give us. We don't take that support for granted. For our first-time visitors, we do really encourage you to subscribe to our channel. We know and we believe that you won't regret it. For those of you who are here for the second, third, or fourth time but haven't subscribed or haven't gained the confidence to do so, please, you're encouraged. We really would use your support. Thank you again for coming back. We appreciate your constant visits, but please make it a bonus to subscribe to our channel. Thank you so much. Going on to the solution, limit of n tending to infinity, the product of n and the integration of n tangent or to the power n of x from 0 to pi over 4. We could begin by focusing first of all on the integration part. So integrating tan n to the power x from 0 to pi over 4 is an interesting endeavor. The first thing I'll do is by letting in be that integration, and such that we can now configure tan to the power nx to tan to the power n minus 2x times tan squared x. And if we go back to identity of sine squared x plus cosine squared x being equal to 1, and if we divide by cosine squared across, we would have now tan squared x plus 1 equal to secant squared or sec squared x, such that tan squared x is equal to sec squared x minus 1. Now, if we replace this tan squared x with sec squared x minus 1, our integration in will be equal to tan to the power n minus 2x times, in brackets, sec squared x minus 1, which is now the product of tan to the power n minus 2x times sec squared x minus tan n to the power n minus 2. Very easy to see from this first term here that this is the same as this integration is the same as the integral of 1 over n minus 1. In fact, the result is n1 over n minus 1 tan to the power n minus 1 x, such that when you differentiate that, you get this first component. And then obviously limit 0 and pi over 4. Minus, just keeping the integral sign here of tan to the power n minus 2 x, right? Now, if we have let in to be integration of tan to the power n, tan to the power nx, this now becomes in minus 2, right? So essentially, we have substituting the limits into that first component, tan to the power n minus 1 of pi over 4, tan to the of pi over 4 is 1, 1 to the power n minus 1 is 1, and then tan of 0, 0, 0 to the power n minus 1 is 0. So we're essentially left with just 1 over n minus 1. And then we'll keep the second part as it is, so that essentially 1 over n minus 1 minus I of n minus 2 is equals to in. So in is equals to, as I said, 1 over n minus 1 minus in minus 2. So if you take in minus 2 on the left-hand side, you get in plus in minus 2 equals to 1 over n minus 1. Okay, so if we do the same process for in plus 2, the tangent of n plus 2 can be configured to tan to the power n x times tan squared x. And so tan squared x can be replaced by sec squared x minus 1. And so that is tan to the power nx times sec squared x minus tan to the power nx. Now we know this. This will result into 1 over n plus 1 tangent to the power nx with limit 0 and pi over 4. And then the second term will remain as it is. So substituting in the limit, we will get 1 over n plus 1 minus the integration of tan to the power nx, tan to the power n x, and then obviously limit 0 to pi over 4. Okay, so as we go forward, you could now decompose this further, but from here, if we pull in, which is now the same as the second component, we can see that in plus 2 plus in is equals to 1 over n plus 1. So this relationship propagates. We saw the relationship between in and in minus 2. Now we've seen the relation between in plus 2 and in. And so there is a relationship there. So if we then play around and then add these two relationships or subtract the relationship we obtained previously, or in plus in minus 2 is equals to 1 over in minus 1 from this relationship in plus 2, we get that in plus 2 minus in minus 2 is equals to 1 over n plus 1 minus 1 over n minus 1. Okay, so and then now if we apply the limits and then multiply n by that difference, we see that the limit of n tending to infinity of n times in plus 2 minus in minus 1 is the same as limit of n tending to infinity of n over n plus 1 minus n over n minus 1. And as we can see, if we divide the numerator and denominator by n, we get 1 over 1 plus 1 over n minus 1 over 1 minus 1 over n. And that means that it is 0. So essentially, the integral of these two, the difference of these two integral multiplied by n and taking that limit is equals to 0. So what that tells us is the limit of n tending to infinity of n times the integral of n to the power n plus 2 from 0 to pi over 4 integral is equals to the limit of, as n tends to infinity, of n times the integral of tan to the minus n to the power 2, tan to the power n minus 2, from 0 to pi over 4. And we can say that is equals to another constant k, okay? So since previously we saw that in plus 2 is equals to 1 over n plus 1, then the limit of n tan n to the power n x plus the integration of tan to the power n plus 2 x 0 to pi over 4 is the same as multiplying n by that. And that means that the same as n times in limit plus the constant which we previously showed to be equal to constant k, which is equal to the limit of n tending to infinity of the product of n times the integral of tan to the power n plus 2 from 0 to pi over 4, and also tan to the power n minus 2 equally, so they are all equal to a constant. We see that we can divide numerator and denominator the same way we did previously. And so this summation here is equals to 1, right? Now, since in plus in minus 2 is equals to 1 over n minus 1, taking the same limit, we can show that the sum of the in plus in over 2 times n, taking its limit as n tending to infinity, the same as limit of n tending to infinity of n over n minus 1, dividing numerator and denominator by n, means that we have the limit of 1 over 1 minus 1 over n, and that summation also goes to 1. So the issue is, now we see that if we add that constant, which is the integral of n tending to infinity of tan to the power n plus 2 or n minus 1 multiplied by n with the limit of n tending to infinity, that constant there, when added to our main integral in multiplied by n, taking its limit from n to infinity, is equals to 1. That summation takes us to 1. So we want to find what in is. And this is where the core of the problem really lies. So one way is to really try to find the difference between the integral of tan to the power nx from 0 to pi over 4 and tan to the power n minus 2. So that if we find a relationship, and here I'm just trying to show that these two integrals are equal, then we would have 2k here, and k would be equal to essentially half. But we have to show that there is equality there. So, and that's why now I'm going forward to try and get that difference. So picking out this integral portion, first I'll let t be equal to tan x, dt dx is equal to sec squared x, dt over sec squared x is equal to dx, therefore dt over tan squared x plus 1 is equal to dx, right? And therefore dt is equal to t squared plus 1 because t is essentially tan x, right? So, and then the limits, when x is equal to 0, t is equal to 0, tan of 0 is 0. When x is equal to pi over 4, t is 1, tan of pi over 4 is 1. So, therefore, the integral of tan to the power n minus x minus tan squared minus x is the same as the integral from 0 to 1 of t to the power n over 1 plus t squared dt minus the integral from 0 to 1 of t to the power n minus 2 over 1 plus t squared. Now, dt over 1 plus t squared comes in as a substitution for dx. And obviously, t to the power n is a substitution for tan to the power n x. And the same applies for t to the power n minus 2, right? So for, because our region of interest is 0 to 1, for that region, from 0 to 1, when t is in between there, it means that t to the power n over 1 plus t squared is less than t to the power n. And that comes from the fact that the denominator here is greater than 1, so the fraction always will be less than the numerator if the denominator is greater than 1. And it is, this fraction is obviously a positive value or real number. And the same thing applies to t to the power n minus 2. This is less than t to the power n minus 2, okay? So the integral, the difference that we're interested in, is also less than the difference between tn and tn minus 2. We can show that by dividing tn minus 2 by tn over 1 plus t squared minus t to the power n minus 2 over 1 plus t squared. We see that we get this ratio that is greater than 1. So meaning that the difference here is a factor of magnitude is greater than, it's 1 times more, it's more than 1 times this difference here. So even if you applied an absolute term here, this inequality would hold. And so going forward, we'll put the inequality sign there. When I integrate this side, as you can see, we get Tn plus 1 over n plus 1 minus Tn minus 1 over n minus 1. Substituting in the limits, we get that integral, the difference is less than 1 over n plus 1 minus 1 n minus 1. Now, if you apply the limit with a multiplication of n, we see that that difference is less than the limit of n tending to infinity of n over n plus 1 minus n over n minus 1. Okay, dividing the right-hand side fraction by n on the numerator and the denominator results into 1 limit as n tending to infinity, 1 over 1 plus 1 over n minus 1 over 1 minus 1 over n. Now, this first part obviously tends to 1, and second part also tends to 1. So essentially, that limit tends to 0. So what this really means is that the limit of n times the integral of tan to the power nx dx from 0 to pi over 4 is equals to the limit of n tending to infinity of n of the integral of tan n minus 2x from 0 to pi over 4, which is equal to k. So since we saw that the limit of in being the integral of tan to the power nx from 0 to pi over 4, that multiplied by n, that limit tending to, as n tends to infinity, plus k is equals to 1. And since we've now shown, at least, that this limit is also k, what that means is that k plus k is equals to 1, and 2k is equals to 1. Therefore, k is equals to 1 over 2. What that means is that the limit as n tends to infinity of n times the product, n times the integral of tan to the power nx from 0 to pi over 4 is a half. And this is our much awaited answer. It was very convoluted, but this is the limit. This is the answer. So thank you very much for hanging out with us. It's been a perfect delight just trying to think through this solution. Yeah, this answer is 1 over 2 half. I hope you enjoyed our thought through that problem. We welcome your feedback, but also if there are other ways to approach the problem, we welcome your feedback as well. Please share with us your solutions and how you think one would go through or about solving that solution, that problem. Thank you again. Until the next problem. À tout à l'heure, à la prochaine fois. Thank you.